All right, guys, let's get into lateral design for steel. This won't be heavy into seismic detailing, but more a general introduction. And then when you take the next classes, we'll get more into like the specifics of moment frame design or brace frame design. So wind forces have a different set of driving parameters than seismic. So this kind of outlines them. Basically, it comes down to weight for seismic and wind speed for wind design. Um, for wind, we want to design things to remain elastic because wind loads happen almost daily, if not yearly. So by that, we say we stay in this elastic range of the curve, of the stress strain curve. For seismic, because those forces happen very infrequently and they're so high, we have portions of the building that we allow to be damaged but remain stable. So what happens in that case when we go past the yield point, there's this huge extension or strain in the material. And if you take the area of that curve, that gives you energy. And since seismic design is all about absorbing energy, this is how we do that most effectively, is to let something be substantially damaged. All right, load paths. We basically start either wind or seismic with some kind of pressure on the wall in the case of wind, or just the mass of a wall. Those loads transfer into the diaphragms, which then transfer their force into the brace frame or shear wall. So the load comes from the face of the building or just mass of the diaphragm into the diaphragms. That moves this way. The diaphragm pushes back by being resisted by the shear wall and brace frame. Those loads create shear through the frame, which essentially creates overturning forces in the foundation and shear at the base of the building. So this from a conceptual point of view, understanding how loads move through the building and down into the foundation will let you understand how to detail all of those interfaces and design those members. Okay, when it comes to diaphragm design, we want to look at diaphragms as deep beams. So if we're looking at a floor in plan view, which is what these images are, we have some kind of wall load or inertial load that creates forces in our diaphragm which are resisted and create reactions into shear walls or brace frames or moment frames. Those forces create tension and compression in our diaphragm just like they do a beam, and then shears. So I think I've got some better slides. Yeah, so if we get into more of the equations, we can calculate the max shear and max moment in a diaphragm just like we do for a simply supported beam. So these equations should look somewhat familiar. And then we like to look at unit shear when we design the diaphragm. So kips per foot or pounds per linear foot. And then we can calculate the tension and compression in the diaphragm just by dividing the moment by the distance between the two chords, so W in this case. Something else to keep in mind is using drag struts and diaphragms. So if you have, if you have a shear wall and we have a metal deck diaphragm delivering load to it, there'll be a stress concentration right at the tip of the wall, which will create high stresses in the diaphragm, which could cause it to start ripping in that location. If we add a drag strut, so maybe a beam or an angle or something that's connected to the wall and connected to the diaphragm, the stresses in the diaphragm tend to be more uniform, and there's far less chance of having a massive failure in the diaphragm. All right, proportions of the diaphragm, there's some span to depth limits. So depending on our flexibility factor, Certain things are not permitted. Certain things are if we have a stiffer diaphragm. Where do we get the F, the flexibility factor? We can come to a table like this. This is from an ICC report. The metal deck manufacturers all have this kind of information. So you can work through what your seam attachments are, what your deck attachments are to the steel below, and then come up with your flexibility factors. Okay, a few little details on diaphragms and drag struts. In this picture here, we can use the rebar in this slab to act as our diaphragm tension and compression elements, or we could use a metal beam, steel beam, and a concrete beam to also act as our drag strut or connector. The key here is we're transferring load from the concrete to the steel with a headed stud. For a drag strut to a frame connection, we can basically just have a top flange connection with bolts, or we could put that on the bottom, just something to pick up tension force from that drag strut or cord and drop it into the beam, or get it across, or a column rather, or to get the force to transfer across the column. A little bit on frame types. This one on the left is a moment frame. This is a brace frame. These are tension only braces. This is at a site, at an industrial site with pretty low seismic loads, and this is at a commercial site with very high seismic loads. Different brace configurations, you can kind of play around with what these look like. Concentric brace frames, the work points will meet at the middle. Eccentric brace frames, the work points will have a separation. So this is nice to give you more opening. I like to use two-story X's as it gives room for doors or ductwork to pass. This is not permitted. We can't have seismic frame configurations where the braces interface at the column middle, or really anywhere along the column other than where there's a beam. The reason for this, it puts high horizontal forces into the columns, which could make them fail. Moment frames, kind of a diagram on the forces and moments inside a frame. If you go back to an analysis class, you can solve these using the portal method, where you assume the shear on the outside columns is half the inside. Solve for the shear, and then you can do small free body diagrams of segments of the frame to find the moments and axial forces in them. In dual systems, sometimes we'll see buildings that have brace frames and moment frames, or moment frames and shear walls. This is a picture of a building that has a perimeter moment frame and then an interior shear wall at the core, which goes up through the whole building. It's not the easiest to see, but there's basically quite a nice shear wall on the inside of that building. It does a lot of work. And the reason we did that was to reduce the size of the moment frame columns so the contractor could get those faster. When we talked about loads, we got into response coefficients, and we use that to calculate the base shear. Those are paired with an overstrength factor and a deflection amplification factor, which are all important for our analyses. It's also paired with these structural system height limitations. So if I have a special reinforced concrete wall in seismic design category D, I can only go up to 160 feet tall with a system like that. C or B, there's no limit. And then there's some cases where they're not permitted. So in seismic category D, an ordinary masonry wall is not permitted. So it's important as you are starting a project to come to a table like this and understand what seismic systems can be used and what seismic systems are off limits. Um, Drift is an important part of this. We want to look at the relative story displacement between floors. So depending on the risk category and the structural system, we have different ratios of height. So in this case, it's 2% of the height is how much one story can move relative to the other. So in this table for different story heights and different criteria, I've calculated what those allowable drifts are. So this is the allowable side. It's important to remember that if you calculate the deflection, which normally we do in software these days, we need to multiply by the C sub D factor, which is given right here. So because we're dividing by R, when we look at deflection, there's actually more deflection than our numbers would tell us. So we take our model analysis, bump it up by C sub D, and then make sure it's less than these allowable values. Different layouts, if we have these horizontal irregularities, so say I have three sides of shear wall or frames, and then maybe a flexible frame here and then nothing, this building is going to perform far worse than a building where we've added frames and we have drag struts in the corners. So as you lay out buildings, work with the architect as early as you can to set things up in a way that are favorable for you. Similarly with brace frames or moment frames, going from brace frame to nothing tends to be a problem. We can make this better by putting in vertical full height braces. Also, taking a brace frame and not continuing it, but continuing it down somewhere else in the plane or the bay can cause high forces coming through here. And sometimes we have to do that, but then we need to design for this frame or this brace member. That force has to transfer through that beam into this brace. So those connections get really burly. Okay, so if we can't meet these requirements to have good redundancy or good layout, then we penalize our systems with these redundancy factors. And you can get into ASC 7 to get more into the nuances of that. All right, something to pay attention to. We've been in the load combinations. We always just write out E, but when you look at E, it actually has two terms, a horizontal and a vertical term. The horizontal term is, anyway, I got interrupted there. So anyway, there's two terms to E. One is the horizontal, which is the base shear times that redundancy factor. The vertical is 0.2 times SDS times a dead load. So this is convenient if you're modeling something just to put an adjusted 1.2 dead plus this 0.2 SDS factor in the load combos. A couple last things. There's a material limit of 50 KSI on seismic material. It's related to fracture toughness. And then there are limits on the flange to the width to thickness ratio of different elements to make sure they remain, that they don't locally buckle and have a reduced capacity from what we expect them to have. So you calc B over T, depending on if you need highly ductile or moderately ductile members, you'll have its acceptance ratio next to it there. This table or something similar to this will give you different acceptability for different sections. So let's say you're designing a special moment frame beam or column. You couldn't use a W36 by 135 because it's not compact enough. So you could use a 36 by 210. So generally when we're designing special moment frames or special brace frames, as we're selecting the members, we'll need to come to tables like this and make sure that the stuff we're choosing meets the compactness requirements. All right, then just a quick look at some types of connections. This is brace frame connection or a concentric brace frame, so the work point of the braces and the beams align. And then there's a bend line, so this can buckle out of plane and the connection doesn't get a bunch of extra stresses in it. Here's a similar bolted connection. And in this case, we could say these ends need to be past the bend line. Or you can design this for an out-of-plane moment and design the gusset plate for that. Eccentric brace frames, the work point is off of the member, usually above in this case. However you look at it, there's basically a gap between the two members where their work points intersect with the beam in this case. And what that does in practice is a lot of yielding happens in this link, and that's what gives us the ability to absorb energy, and then hopefully it's fairly easy to repair. And then moment connections, here's a heavy bolted connection, and then the dog bone connection came after the Northridge earthquake. The theory is if you have a full pen weld, because if you have a reduced section, the beam will yield right here and reduce the demand on the welds. They still suck, so there's better connections than these, but they're used quite a bit. Weld access hole, AISC has a definition on all of the geometry here, so now if you call that out as an AISC weld access hole for seismic connections, then the detailer will know how to lay that out. All right, and then we have, in connection design, we will often refer to using the expected strength. So when you have different materials produced at the mill, depending on the standard they're made to, there may or may not be an upper limit on yield strength. So A36 doesn't have an upper bound limit. A992 does. And so if we say design a connection for the expected force from the brace, and it's a A36 brace, we'll increase the yield strength 50% to make sure we have enough force in that connection in case what comes out from the mill is such high strength material, we still have the ability to design a connection that's strong enough for it. All right, then the last slide here are protected zones. So in special brace frames, special moment frames, and special eccentric brace frames, there are areas where we expect the yielding to occur. And in those areas, you can't have connections other than pre-qualified connections, notches, or any arc strikes. And the reason for that is because there's so much plastic deformation going on in the yielding, any arc strikes or notches will start cracks and end up fracturing the connection. So in those zones, generally, it's good to call those out to be painted like a bright color so the people working in the field can say, oh, that's something I need to stay away from. All right, that wraps up intro to lateral design. Plenty more to be said, but for now, we will leave it for class time.